Zabb-Parmley.
And today we're going to discuss the removal of stormwater contaminants in wetlands and biofilters.
So I want to start off by introducing our project leaders. Dr. Stan Grant, who's our principal investigator. He kind of ran the whole operation while in Australia and ran the whole operation in general. He helped us with sensor data while we're at each site. Dr. Megan Ripley, she's our research specialist, so she helped us with statistical data analysis as well as TSS and chlorophyll analysis. Dr. Sunny Jiang is our pathogen specialist. She helped us determine water quality in terms of pathogens in the water. And Dr. Andrew Marion, who's our ecology specialist, he helped us identify invertebrates and plants while we were there.
Our objectives were to better understand the effectiveness of biofilters and constructed wetland in removal of stormwater contaminants. We compared the inlet and outlet contaminant concentrations to assess differences in removal efficiency and identify the best system to remove each pollutant. Where available, we compared the contaminant concentrations to Melbourne water classing standards.
So we looked at biofilters and wetlands while we were there. We determined that there were 4 key differences between the two. Their design, with the way the water flows through them, how they're applied, and how effective they are in removing the different types of pollutants. So looking at wetlands, constructed wetlands mimic the function of natural wetlands in that they filter water horizontally, as you can see by the diagram right there. They're mainly inhabited by riparian species. From the plants, this includes rushes, sedges, and grasses typically. And they serve as a buffer between land and aquatic environments. And this kind of attributes to the high level of biodiversity seen in these systems. Looking at biofilters, they filter water vertically through a set of layered filter media, each is specifically designed to filter out pollutants. Because of this, they are much more compact and space efficient, and they can be pretty much anywhere. The effluent or the output of the biofilters is poured into a perforated pipe where it can be further treated or stored in an underground basin.
Moving on to our methods. In Australia, we visited 5 sites, 2 biofilters, Wicks Reserve and Hereford Road, and 3 wetlands, Hampton Park, Lindbrook Estates, and Royal Gardens. At each different site, we took water samples, which we took back to the lab to analyze in order to measure total suspended solids, E. coli, and chlorophyll. In addition to the water samples, we also took sensor to measure different parameters for water quality. And we decided to look at specifically dissolved oxygen. On the next slide, you can see the different sites that we visited, and we mapped out where we took the samples. And the way we went about sampling is we divided each site into inflow and outflow, and middle cross sections or transects, which you can see here. For the purposes of our group, we averaged the values of the inlet and the outlet in order to compare how the different parameters change in each water filtration system. Moving on to our results a little bit, we wanted to compare the parameters we measured with Melbourne's Class C water standards. These standards are for non-potable water, so non-drinking water, or water used for irrigation of crops and agriculture. The 2 parameters we analyzed or compared to the Class C standards are total suspended solids and E. coli. E. coli being a good indicator of fecal contamination.
Total suspended solids are a combination of silt, decaying matter, amine, and industrial waste and sewage. The Clean Water Act classifies total suspended solids as contaminants, as pollutants. Constructed wetlands and biofilters are designed to reduce total suspended solids and increase dissolved oxygen. Here are our TSS results in bar graphs. On the y-axis, you can see total suspended solids measured in milligrams per liter, and the x-axis has a sites example. The red horizontal line indicates the Class C standard set at 30 milligrams per liter. Both biofilters were successful in significantly reducing total suspended solids and meeting the Class C standard. Lindbrook and Royal Gardens wetlands, as you can see, have large errors and that overlap each other, making this data unreliable, and we cannot conclude that the change in TSS is significant. Hampton Park had 2 inlets A and B constructing the wetland, and the data indicates a large increase in total suspended solids that actually does not meet the Class C standard. Microbial contamination in water sources is typically caused by fecal matter, and they are high risk for public health and need to be monitored to abide by regulation. The Class C standard for E. coli is 1,000 all uniform units per 100 milliliters. Constructed wetlands and biofilters can effectively reduce E. coli or bacteria like E. coli up to 90%. Rural gardens showed significant decrease in E. coli, meeting the Class C standard. Lindbergh actually started and ended underneath the limit, but was successful in removing more than 50% of the original E. coli. Hampton Park was also under the limit, but actually showed a remarkable increase. This could be a result of biodiversity, so that wildlife living on the lake could have contributed to our high ratings. Both biofilters that we sampled showed trivial count of E. coli.
So moving on to chlorophyll, I just want to point that on the y-axis, you'll see chlorophyll in micrograms per liter. On the x-axis, we have all the sites that we sampled at for inlet and outlet. So looking at the chlorophyll data, you'll see that in the wetlands, there's a general increase in chlorophyll levels between the inlet and the outlet, whereas in biofilters, there's a general decrease. Hereford Road is an exception. There is no significant difference between the inlet and the outlet. But we attribute the difference in trends between wetlands and biofilters partially to the flow path that the water takes throughout these systems. So in wetlands, the water travels horizontally and therefore it receives a greater exposure to sunlight, driving photosynthetic activity and increasing chlorophyll levels. For biofilters, water filters vertically into the ground and does not receive much sunlight exposure. Therefore, you see lower levels of chlorophyll. It's for this reason that we recommend biofilters be used instead of wetlands in areas where algal blooms are concerned to the surrounding community.
The final parameter we looked at was dissolved oxygen. DO is actually a really good indicator of water quality, so we want to see how it changed in these water filtration systems. When we looked at the wetlands, the inlets actually had pretty high levels of DO. And what was surprising is that the DO levels actually increased. A lot of these wetlands, they have large ecosystems, which a lot of these organisms consume a lot of DO. So we expected the DO levels to go down, but the fact that at every wetland the DO increased shows that ecological systems can thrive in these wetlands, which is really adds an aesthetic purpose to these wetlands. As for the biofilters, we had an interesting trend. Wicks Reserve, the outlet was in a subterranean sump, and the DO was very low. As for Hereford, the outlet was a creek, and the DO level was very high. This shows that subterranean outlets and biofilters made lower DO levels.
So this slide, we compared chlorophyll and dissolved oxygen to kind of highlight the relationship between the two. You note that high levels of chlorophyll are accompanied with high levels of dissolved oxygen at the outlets. Based on this data, we can conclude two things. One, that these outlet environments are definitely not eutrophic, and two, that there's an accumulation of phytoplankton occurring here. Keep in mind that this data here is a snapshot of these specific wetlands in a specific moment in time, and it could vary by week even. This is an area that warrants research, and we're really interested in seeing what would happen if we took further measurements.
We hope that by studying Australia's wetlands and biofilter systems, that we can take what worked and learn from what didn't work and apply it to Southern California, where we mostly rely on Northern California and other regions for our water supply. The hope is that it won't take a severe drought to change public perception regarding recycled water. And with that, we would just like to say thank you.
Questions? Peter?
I had a quick question. You know, if you looked at a 24-hour cycle, a diurnal cycle, a couple of them so you could do statistics on a biofilter versus a natural wetland. In a natural wetland, it can be either driven dominantly by autotrophic or respiratory processes. But it's looking for your data as if in a biofilter, particularly since there isn't that much photosynthesis, it would probably be respiratory, right?
of dissolved oxygen are consistent throughout each wetland, despite having been sampled at different times. So it could be prescribed trouble.
Well, we did sample just during the day, and so I think Peter's point is that if you went into, and we sampled at night, which would be really fun.
Yeah.
You might see a different, yeah, one thing you have bites all over your body.
Right.
We spend all of our nights in the lab. Any other questions? All right, let's give him a hand again.